So the last time we were just looking at this, sorry, looking at this. Now you can write your dynamical system in this way. Let me change colors. So first, you're gonna have 1 divided by CT equals beta expectation of, let's say, QT plus 1. So here, QT is the derivative of the value function with respect to K, okay? All right, so we define Q in this way. So QT plus 1 is here. Of course, we are taking the expectation. Then you have QT equals beta times alpha lambda KT alpha minus 1 e to the ZT expected value of QT plus 1. And then you have the resource constraint, okay? E to the ZT lambda KT alpha minus CT, right? Now, in this particular version, you can either work with this one, which is what we typically do, right? So we don't have to deal with discretization. We can assume that Z can be continuous. So this defines these 4 equations define your system. So remember that you had this function, right? That defines your optimal path. So here you have your control variables. So in general, you write them in this way, QT, and then you have the states, right? You have the states. And you can write all these equations in this way, but here, obviously, you have to take the expectation. Okay? Because you have forward-looking variables, right? Such as these ones. So then you can use the perturbation methods to approximate solutions. In practice, most people use Dynair. So Dynair is a particular MATLAB toolbox, okay, which is very useful. So you can, if you want to learn more about the practical applications, you can check how Dynair is used. Or there is also this toolbox by Schmidt-Grohe and Uribe. Okay, so remember their 2004 paper in Journal of Economic Dynamics and Control. In that paper, they developed this idea theoretically, and they also provide a toolbox. For long years, I used that toolbox for solution because I've been at Duke, and Martin Uribe was using his own program, so I used his toolbox. But you can also use Dynair. Dynair's advantage is this, so you can also estimate models with Dynair. Okay, so that's for the practical applications. Okay, now let's look at an example, which is a very simple job search model. Okay, so the idea is this. There's a worker. This worker wants to maximize the lifetime income. Okay, net earnings, let's say. ET here is net earnings. So the control can be two things. Search for a new job, or do not search for a new job, all right? So for notational simplicity, let's denote them by S and N, okay? And the state space is this. So the wage will be the state variable, okay? Wage will be the state variable, and there are three wage levels in the economy, okay? So one wage is the highest one. Another level is the medium one, and there's also this WL, okay? And the search cost is kappa dollars, search cost. Okay, so this is how it works. If control is equal to S, net earning is equal to what? WT minus kappa, because now there's the search cost. If CT is equal to no search, then it is equal to WT, because consumer, the worker is not searching for a new job, right? To complete the description of the economy, we have to talk about the state, right? Transition equation. So here's the idea. So there's WT, there's WT plus 1. So here we have WL, WM, and WH. Here we have WL, WM, WH, okay? So obviously I'm talking about a Markov transition probability matrix, okay? So these are PLL, PLM, 1 minus PLL minus PLM. This is PML, PMM, and 1 minus PML, PMM. Okay? And here you have PHL, PHM, and 1 minus PHL, PHM. Okay? Now, for this particular problem, since I want to do it very simply, I assume that this Markov matrix is equal to this. So if you are a low-wage worker, you remain low wage. Okay, if you are a high-wage worker, you remain high wage, regardless of the search. But then, if you are a medium-wage worker, you either become a low-wage worker in the next period or high-wage worker. Okay? This is, of course, conditional on search, right? If you do not search, so this is conditional if CT is equal to search. If CT is equal to no search, then WT plus 1 will be equal to WT. Okay? So that's the idea. And that's very simple. As you know, there could be an alternative case. For instance, you may have this. You may have, for instance, this would be slightly more difficult. Okay, so here, if you search as a low-wage worker, there is a probability that you become a medium-wage worker. And here, if you are a high-wage worker, there's a probability that you become a medium wage worker, okay? Because you quit your job, I mean, you basically terminate your job and find a better wage or a lower wage, okay? So there is risk involved in this case, okay? And here as well, right? Because a medium one can become a low wage worker. And here, of course, there is a return as well, but this is a risky return. Anyhow, so how do you solve this problem, right? Now the intuition suggests very quickly that if the worker is a high wage worker, right, he wouldn't search, right? Because, of course, I am looking at this case for this example, the simplest one, all right? So if I am already high wage, okay, and if I search, I will still be a high wage worker. So there's no point in searching for a new job. The same is true for the low wage worker. If I am already a low wage worker, even if I search for a new job, I cannot find a new job with a better pay, all right? So for, so if WT is equal to WL, then the intuition suggests that there should be no search. Similarly, if W is equal to WH, then no search would be optimal, all right? Then we can actually do this. We can calculate the value of being a low search worker. Now, what's going to be, since I'm not searching for a new job, I do not pay the cost, right? So ET is equal to WL, here ET is equal to WH. So at the end, my wage remains the same, right? Without search and with the, since there's no search, WT plus 1 will be equal to WT, all right? So then from this, I know the value of becoming at this state, of being at that state. And then I also know by the same reasoning, under no search, the value of being a high wage worker will be equal to that. Because we are executing this policy of no search for the rest of the history. Okay. Now, of course, the situation is different in this case, right? Why? Because now I have a possibility of attaining a higher wage. All right. So let's try to understand that. Let's try to understand that. So if I search, so okay, if my wage is WM, and if I search, then what do I have? I have WM minus kappa, right, plus beta. Now here, I want to write the expected value of what? I want to write the expected value of my wage conditional on the fact that WT is equal to WM, right? And if I do not search, then I will have again this. Okay. Now notice that this expectation, sorry, this is wrong, right? So the correct one will be, let me show you. So this is wrong because I forgot the value function. So it will be like this. So okay, expected value of the value function of WT plus 1, conditional on the fact that WT is equal to WM. Okay, and here, notice that we have the same thing. Okay. Now, how do I proceed? Well, I have this, right? So I have Wm minus kappa plus. Now be careful. I'm looking at this actually. Oops. So I'm looking at actually at this. So this expectation is like 1/2 VWL, right? Next period, my wages WL or my wages WH, okay? This is in the case of search. In the case of no search, obviously my wage is WM, all right? So what do I compare? What do I compare? I'm comparing this with this, right? Now, this is equal to what? This is equal to that, okay? So I choose to search only if when? I choose to search if this is greater than that, right? That's the only meaningful way of deciding on whether we search or not. So what do this require? Let me write it again. So wait. Yeah. So I have again Wm minus kappa. This is under the case of searching. WL plus WH divided by 2. Now I want this to be greater than VWM minus beta, right? Now notice that, recall that VWL will be equal to what? Because once the worker transits to the low wage or high wage, he or she will stop searching, right? We know that. So this will be VWL divided by 1 minus beta. And this is WH divided by 1 minus beta. And similarly, this is the case of no search, obviously, right? So in the case of no search, this will be equal to that, right? It will never change. So what do we have then? We have Wm minus kappa plus beta, WL plus WH, 1 minus beta 2, right? greater than Wm 1 minus beta. Okay, is that correct? So there's no 1 minus beta here. That's also a mistake. Okay, so this will be simply V no search Wm. Okay. So what does this tell you? Well, it tells you that at the end, if you do the math, I'm not going to do that, it will tell you that kappa will be less than this. Okay, so what does it, so this part is the expected wage, right? So this is expected new wage. So if this is greater than Wm, and given that your discount factor is large, you're gonna search. Okay, so your search cost, given the wage levels in the economy, if your search cost is sufficiently low, then you're gonna search for a new job, because if you are a middle wage worker, medium wage worker, then there is a possibility that there's a probability that you're gonna find a higher paying job. Okay, but that decision, of course, depends on what's the expected wage, what's your current wage, and what is your discount factor. Okay, so the search cost, if it is sufficiently low, any medium wage worker would search for a new job. Okay, some would find them, some wouldn't find them. Okay, that's a stochastic outcome, but for policy function, it doesn't really matter, right? Because it all works with the idea of expectations. Now, the other version of the problem where, where's that? So in the other version where you have this transition probability matrix, the solution is much more difficult. I'm not sure, even perhaps you cannot, maybe you cannot find the analytical solution, but you try, work on this with the same logic. Okay, in that case, you're gonna find policies for low and high paying, low wage people and high wage people as well. Okay, but the idea is the same. Okay. So any questions about this? So as you see, sometimes the state space is discrete, right? So you want to use your Bellman equation in a very simple and intuitive way. All right. So the last thing I want to cover is this. I want to show you a simple example of another stochastic problem. Where's that? I cannot find it right now. Where are you? So you have no questions about any of this? Good. That's very nice. It saves time. For some reason I cannot find. Oh, okay, I found it. Now this is a problem where so let me show you. So there's a problem. So let's suppose that there's this research technology. All right. So if you spend some amount of money to research, so this amount.
Sorry, you forgot to share your screen.
All right, great. Thank you very much. Okay. So let's suppose that with gamma some positive number, there is this research technology, all right? And that research technology does what? Well, it increases your utility somehow, right? So there is a utility function. So here, of course, I mean, why spending money on research increases your welfare? Well, because, you know, behind the scenes, there is an endogenous growth model, as in Romer model or Lucas model. So spending money on research or human capital, so whatever that engine of growth is, so spending money to that technology increases your welfare. But in the meantime, so let's put some parameter here. But in the meantime, it creates a danger, all right? So the danger works in the following way. There is this variable dt, okay, so here alpha is positive. So there's this variable dt, okay? It will be equal to 1, sorry, it will be equal to 0. Let's say it will be equal to a number very close to 0, okay? Let's put a parameter there for specific, you know, a specific parameter. So eta, it will be equal to eta with probability mu RT, okay? And it will be equal to 0 with the respective probability 1 minus mu RT, okay? Now, mu RT is this function, theta RT squared, okay? So eta is less than 1, but very close to 1. Okay, theta greater than 0, all right? Now, what's happening here? Let's try to understand that. Well, if I spend more money on the research technology, that increases my welfare, but it also creates a danger. What type of danger is that? It is stochastic, okay? So there is this probability mu, with some increasing probability, dt is equal to a number that is very close to 1. So this will be very close to negative infinity, all right? Because this number will be very close to 0, okay? So this creates a punishment. Let's say this is a nuclear technology, all right? So it increases energy efficiency, but it also creates a danger such as Chernobyl or Fukushima, right? So that's the idea. Then how to choose the research technology? With other probability, 1 minus mu, there's no danger, right? D is equal to 0, then ln 1 is equal to 0. Okay? So that's the type of the problem that we want to. So, oh, by the way, sorry, this is dt plus 1. I'm sorry. So this is the transition equation. So this is dt plus 1. All right. So that's the notion. So how do we choose how much to spend on this research technology if we have this problem? So there is this, yes, we want to increase our welfare from an economic point of view by using this technology, but technology creates a danger to human life, or it creates a danger to environment, it creates a danger to for the planet. All right. So here is the idea. Obviously, there will be a Bellman equation. Bellman equation will be a function of state. So we want to maximize this. Of course, it is alpha ln RT, okay, plus ln 1 minus dt plus, careful, let's say you have the discount rate, and here you have the expected value of that. Okay. So how do we approach this problem? The idea is this. I know that dt plus 1 will be either equal to 0 or eta, right? Because that's the state space. So I can actually write this in this way. Maximize alpha ln RT ln 1 minus dt plus beta. Now I want to write this expectation. How do I write this expectation? Well, very simple. With mu, with probability mu, it will be equal to what? It will be equal to eta, right? So I have this. And with probability 1 minus mu RT, it will be equal to 0. Okay? There you have it. And you are choosing RT. Okay? Now you can do it. Why? Because the so you have this. You have, let me iterate one more time. You have alpha ln RT plus ln 1 minus dt plus beta. Now careful, you have mu RT V eta minus V0 plus V0, right? That's the continuation value. And this is theta RT squared, right? So if you take the derivative, so if you take the derivative with respect to RT, you're gonna find something like this. You're gonna find alpha RT plus beta V eta minus V0 to theta RT. Okay. And suppose that RT is interior. Okay. Suppose that RT is interior. Now you have RT equals or RT square equals alpha divided by beta 2 theta and V0 minus V eta, right? Because this is positive. All right? Then now you're gonna find, where am I? Okay, then you're gonna put, so now you know what mu RT is, right? Because it's theta RT squared. So you have alpha divided by 2 beta V0 minus V eta. Okay. We have about 3 minutes. So let's take one very quick break because I am already done. I'm almost done with this problem as well. Let's take, by the way, let me check the conversion. Okay, so that is converted. All right, so it is 27. So let's meet at 3:40. All right, for a final half an hour, so that we can conclude. All right.
Okay.
All right, so let's meet at 3:40, and we're gonna conclude our class.